For alternating series that converge, there's a really nice theorem that'll tell us, if we look at the difference between the true sum and the partial sum, it'll tell us the error in that estimation. So this formula is really nice. It turns out the difference between the nth partial sum and the true sum is going to be no more than the n plus 1 term in this sequence. Okay, so for example, if I wanted to find the 100th partial sum, it would be off by no more than the 101st term in the sequence. Okay, so this theorem states that as the absolute value of s minus s sub n. Okay, so the magnitude of the error between the true sum and a partial sum is less than the n plus 1 term in the sequence. All right, so we're going to start this out. We're going to approximate the sum of the alternating harmonic series using the first 9 terms. So we're going to actually find S9 and then we'll figure out what the error is in that calculation. My b sub n here, I'm going to strip off my blinker. So my b sub n is just 1 over n. So S9 is going to be the first 9 terms. So 1 minus a half plus a third minus a fourth all the way out to 1/9. And that's going to be approximately equal to, if you punch that in your calculator, about 0.7456. Okay, and for the error, we're going to do the magnitude of s minus s9. That's going to be less than b10. Okay, so there's the n term, there's the n plus 1. Okay, so this is going to be equal to 1/10. Or 0.1. So this estimation is off by no more than 0.1 from the true sum. All right, let's take a look at number 6. So we're still going to stick with the alternating harmonic series, but now we want to see how many terms will it take so that we get an error less than 10 to the negative 3, so less than 0.001. Okay, so my b sub n is still this 1 over n, and I'm going to do s minus Sn, I'm looking at the magnitude of that, is going to be less than b sub n plus 1. And I can find this term by plugging this capital N plus 1 in. So I get 1 over n plus 1. I need that to be less than or equal to 10 to the negative 3. So I'll divide the 10 to the negative 3 over to the other side, multiply the n plus 1 back. That gives me 1,000 is less than or equal to capital N plus 1. Which means capital N is greater than or equal to 999. So if I use 999 or more terms, I'm guaranteed that the partial sum will have an error of less than 10 to the negative 3. All right, and then one last example, we're going to use a different series this time. So I have negative 1 to the n over 2n plus 1, and we want to be within 1/15 of the true sum. Now my b sub n here is 1 over 2n plus 1, taking that blinker off. And we'll start out the same way. So the formula is the true sum s minus the partial sum sn, we're looking at the magnitude of that, is less than the n plus 1 term in the sequence. So I can plug this n plus 1 in, and I get 1 over 2 times n plus 1 plus 1. And I want that to be less than or equal to 1 over 15. So I'll simplify this. This gives me 1 over 2n plus 3 is less than or equal to 1 over 15. If I cross multiply, I get 15 is less than or equal to 2n plus 3. If I solve that, that gives me 6 is less than or equal to n. So if I want to be within 1/15 of the true sum, I need to pick an n that is at least 6 or bigger. All right, so that is how we use the alternating series estimation theorem.